Welcome to the Explainer. So today we're literally putting on our detective hats and diving headfirst into a really thrilling geometric investigation. We're going to unlock the secret rules of shapes, focusing specifically on this incredibly fascinating chapter all about four-sided figures. I mean, if you've ever looked at a blueprint or, even just a basic window frame and wondered exactly what invisible mathematical laws hold it all perfectly together, well, you are in the exact right place. We are going to use the clues hidden right in plain sight to deduce the properties of these shapes.
Okay, let's just get right into it with our foundational definition. Before we can actually be shape detectives, we kind of need to know the name of our prime suspect, right? Quadrilateral. Now, I know it sounds super complex, but if we break down the Latin roots, it instantly demystifies the whole thing. Quadri simply means four, and lattice refers to sides. So basically, any closed, two-dimensional shape with exactly four straight sides, that's a member of the quadrilateral family. Simple enough for sure. But as we're going to see, having four sides is really just the entry ticket. The real magic, that lies in how those sides actually interact with each other.
To really anchor our investigation in the real world, I want you to step into the shoes of a carpenter for a second. We call this the carpenter's problem. Imagine you need to put together two thin strips of wood so that when a thread is passed tightly around their endpoints, it forms an absolutely perfect rectangular frame. The catch? You're not looking at the outside edges yet. You literally just have these two intersecting strips that will act as the diagonals. So how exactly do you construct this to guarantee the final shape is a true rectangle? This specific puzzle is going to guide our entire geometric journey today. So here is the roadmap for our investigation today. First, we'll meet the quadrilaterals, then tackle the carpenter's problem, decode the diagonals, dive into parallelograms and rhombuses, explore trapeziums and kites, and finally bring it all together with the complete quadrilateral family. All right, let's kick things off. Section 1. Meet the quadrilaterals.
Now, while the four sides are obviously important, the true identity of these basic shapes, like our totally familiar rectangles and squares, is really defined by their internal angles, the spaces between the sides. In a rectangle, the absolute rulebook clearly states that all the internal angles must be right angles. That means exactly 90 degrees. Plus, the opposite sides absolutely must be of equal length. That is the fundamental rule they follow to exist.
Moving right along to Section 2, the carpenter's problem.
Remember, our carpenter only has two diagonal strips of wood to define this whole frame. To ensure it actually becomes a perfect rectangle, they have to make three logical geometric deductions. First, what does the length of the second diagonal strip need to be compared to the first? Second, where exactly should these two strips intersect? And third, what should the angle be between them when they actually cross? Now, these aren't just random guesses. They are highly precise geometric rules that we can figure out together.
And get this exact geometric deduction isn't just some abstract idea stuck in a textbook. It's a method used practically all over the world. Carpenters in Europe use it, and wonderfully, farmers in Mozambique use this exact same method when laying out the base of their houses to guarantee a perfectly rectangular foundation. How cool is that? It just proves that this kind of mathematical reasoning is literally vital, real-world engineering. Which brings us to Section 3, decoding the diagonals. So, through some clever geometric deduction, we finally get the exact answers for our carpenter. For a shape to actually be a true rectangle, its diagonals absolutely must be of exactly equal length. Furthermore, they have to bisect each other, and bisect simply means they cut each other exactly in half. Therefore, the exact point of intersection has to be the dead center perfect midpoint of both strips of wood. If the carpenter nails this, the thread wrapped around the ends will perfectly form a rectangle. Mystery solved. And honestly, this brilliantly illustrates how geometric constraints can totally change a shape's identity. Just think about the comparison. A rectangle's diagonals are equal and bisect each other, right? But if you take those exact same diagonals, ensure they are equal and bisecting, and then force them to intersect at exactly a 90-degree right angle, boom, the shape completely transforms. It becomes a square. Not only that, but in a square, those diagonals act as perfect dividers, cutting the 90-degree corner angles exactly in half into crisp 45-degree angles. So really, a square is essentially just a rectangle that decided to follow even stricter rules. Okay, let's dive deeper. Section 4, parallelograms and rhombuses. Now, as the name kind of gives away, a parallelogram has opposite sides that run completely parallel to one another. But what's super cool is that this creates a really beautiful, predictable mathematical rhythm on the inside.
Because of transversals crossing those parallel lines, any two adjacent angles, the angles sitting right next to each other, will always add up to exactly 180 degrees. And the angles sitting diagonally opposite each other, they are perfectly equal. It is just a stunning example of geometric symmetry. And that brings us to the rhombus. A rhombus is a quadrilateral where all four sides have the exact same length. But here is the real secret. Because its opposite sides are parallel, a rhombus is actually just a very special type of parallelogram. You can basically think of it as a parallelogram that was somehow forced to have four perfectly equal sides. Let's break this down further and see how this builds our understanding. We're going to use our trusty diagonal lens again. Because a rhombus is technically a parallelogram, it naturally inherits its rules, meaning in both shapes, the diagonals bisect each other. Makes sense. However, the rhombus gets a major upgrade. Because all four of its sides are equal, its diagonals don't just bisect, they intersect at exactly 90 degrees. A standard parallelogram simply does not have that strict 90-degree rule for its diagonals.
Up next, Section 5, Trapeziums and Kites. So let's look at the trapezium. A standard trapezium's main defining rule is that it only has one single pair of parallel sides. And, well, that's it. However, if we look at it through the lens of side lengths, we find a really special variation. An isosceles trapezium still has that one pair of parallel sides, but it adds a totally new rule. The two non-parallel sides must be of exactly equal length. This gives it a beautiful, balanced symmetry that's actually very much like an isosceles triangle. And then we have the kite. Now, the kite plays by an entirely different set of rules when it comes to its equal sides. Unlike a parallelogram where the opposite sides are equal, a kite has equal sides that are adjacent, meaning they're uniquely placed right next to each other. It has two pairs of these equal adjacent sides, and importantly, they do not overlap. I mean, it quite literally looks exactly like the kite you'd go fly in the park. Now, here is an absolutely crucial number to remember for our geometric investigation: 90 degrees. We've seen this number pop up again and again when we look at how diagonals intersect. When diagonals cross at exactly 90 degrees, we are looking at some highly structured shapes. We proved this for the square, we proved it for the rhombus, and, fascinatingly enough, this strict 90-degree intersection angle holds completely true for the diagonals of a perfectly constructed kite as well.
Finally, Section 6, the quadrilateral family. Let's bring it all together. Let's quickly review the rhombus to see how it all fits. It perfectly shows how just one shape can borrow properties from broader categories. Think about it. Because it's a parallelogram, its opposite sides are parallel, the adjacent angles total 180, and the opposite angles are perfectly equal. But because it has equal side lengths, its diagonals bisect at perfect right angles and actually slice the corner angles right in half. It is a beautifully complex shape built entirely from simple overlapping rules.
And honestly, this brings us to the absolute most powerful concept of the entire chapter. It's like a giant Venn diagram of shapes. Think of it as a strict hierarchy of geometric rules. Adding constraints basically filters broad categories down into much more specific shapes. For instance, a basic parallelogram with equal sides becomes a rhombus. A rhombus with 90-degree internal corner angles, that becomes a square. That literally means every single square is technically a rhombus, and every single rhombus is technically a parallelogram. It really is all about just how many rules the shape follows. So I'm going to leave you with this final, totally provocative question straight from the chapter, and it's designed to really challenge your newly honed investigative skills. Based on all the rules we deduced today about side lengths, angles, and diagonals, is it possible? Can there be a quadrilateral that perfectly satisfies the rules of both a kite and a rectangle at the exact same time? Just think about the adjacent sides of a kite and the 90-degree angles of a rectangle. I highly encourage you to grab a piece of paper, sketch it out, and see what you discover. Thanks so much for joining me on this explainer, and hey, keep exploring all the shapes around you.